Okay, good morning everybody. If you remember, the last couple of lectures were spent on the idea of detecting key points. I should say we spent quite some time studying the idea of investigating properties of surfaces. And well, if you look at, again, for simplicity, intensity image, we can think of this as a function defined over two variables, x and y. For every x and y, we would have a z value, and the collection of those z values defines some sort of surface. And we looked into the idea of studying properties of these surfaces. Turns out that you can actually theoretically find out a lot about the nature of a certain surface just from investigating its local properties. That is, from looking at certain differentials in the vicinity of every point. Of course, in our case, the digital images, this has to be taken with a grain of salt because that theory has been developed or is valid for continuous surfaces. Of course, the digital images we are dealing with are discrete functions. That is, we have a discrete domain, just a couple of possible values for the x-coordinate, a couple of possible values for the y-coordinate. So it's discrete, and therefore we have to be careful. Nevertheless, we can, as we often do, pretend that in a first order approximation, these discrete images we are dealing with are continuous, and we just use all these methods anyway. What we are going to study today has to be seen under that caveat as well, right? I'll be beginning with refreshing something we very briefly discussed in the last semester. And in the context we're discussing or studying right now, it will likely make more sense than it did in the first installment of that course. And again, last time, not last semester, but last time, we discussed key points and had a look at corners, which we understood as points on that surface where the surface is bent somewhat extremely, as a high curvature. But I already said that depending on the kind of application context we are dealing with, key points do not necessarily have to be corners or points of high curvature in the image, but maybe also indicate block-like structures. This is what we are going to study today. But in order to be able to understand that, we have to remind ourselves of the notion of the Laplacian. Let me see if that one looks better. No, well, Laplacian of Gaussians, or the idea of difference of Gaussians. And funnily enough, this time the Gaussian again refers to the probability distribution, not to the idea of Gaussian curvature. That one looks better. As always, we assume that we are given an image, and I shall call it f of x and y, and again note that I'm using the parentheses rather than squared brackets. So I pretend the image was a continuous function, right, defined over a continuous domain. Let me also ever so briefly recall the definition. The bivariate Gaussian, I shall denote it using a capital G with a subscript sigma. This is of course also a function in our context, bivariate Gaussian. defined over two parameters or variables, x and y, and it is given by 1 over 2 pi sigma square times e to the minus x square plus y square over 2 sigma square. And we are all well familiar with the idea of using this Gaussian in an operation called convolution. And when we use a Gaussian to convolve an image, that is to say that we compute a smoothed version of the image, or a filtered image. Let's call it smooth, is a nice idea. Smoothed image, and I will call this one G of x and y, and this time I will also pretend it was a function of sigma, because, well, it actually is, never made it explicit. If we convolve the image f of x and y with the Gaussian g of x and y, which has a third parameter, namely the sigma, which plays a crucial role or important part in the definition of the Gaussian, well then of course the result g of this convolution, of this smoothing operation, will look different for different choices of sigma. I have never made that explicit so far in all our lectures up until today. This is the first time that I include the sigma as an explicit parameter of the smooth image G. And while I clean the whiteboard, I urge you to convince yourself that that actually makes sense, that this result really depends on our choice of sigma. Up until now, it did not really matter for our discussion in all our lectures in image processing 1 and 2 so far, but today it will come in handy to understand this resulting image as a function of 3 variables. Now, I guess it was during the last lecture that I ever so briefly recalled the notion of the Laplacian. Again, this is something we studied more or less in detail, not really quite in detail, but we already studied it in image processing 1. So let me just briefly remind you of the definition. So this is nabla squared, which is to say the inner product of the nabla operator and the gradient of G. We may also write this using this delta G. So this is called the Laplace operator, and is to be understood as this. So this has to be understood as we compute the gradient of G, and we, compute the inner product of the gradient of G with this operator. This is doable. We can, these operators are linear operators, so we can use them in the context of, say, inner products. So for those of you who find that fishy, there's no problem here whatsoever. And if you do not like this idea where it comes from, then let me just tell you, if you compute this, what you find in the end, that this is just gxx plus gyy, where this is supposed to be the second derivative of g with respect to x, and this is the second derivative of g with respect to y. We have to add that. And the reason why I already ever so briefly mentioned the Laplacian in the last lecture is that given what we studied back then, we can now actually express the Laplacian of such a function. In our case, again, the spatial domain is just two-dimensional x and y coordinate. can express that as 2 times h Gaussian curvature. Right, so h is Gaussian curvature. This is of course interesting because it tells us that the Laplace operator somewhat implicitly is tied to the notion of curvature. Right? And we were interested in studying curvature from the point of view of finding certain characteristic locations on a surface. Now, again, last time I ever so briefly said, and I'm not actually going to prove this, but we discussed it with respect to h, the number that indicates Gaussian curvature, that this is invariant under rotation. And by that I mean that if we consider the image G to be defined over a set of coordinates x and y, and we compute the Laplacian at some point of the function g of x and y, somewhere here, it doesn't matter if, I don't know, we have chosen that x and y or some x prime y prime. With respect to the second derivatives, you know, they depend on our choice of the coordinate system, but here we have, this produces a scalar, we add 2 second derivatives, and this scalar does not depend on our choice of the coordinate system. So this is an invariant property of a surface, which is great, because you know, that tells us that if we take a picture, and I don't know, take a picture of the same scene where the camera is slightly rotated, if we were to compute the Laplacian for every pixel, it should be more or less the same. Of course, it will not be exactly the same, once again, because images are discrete structures, whereas all of this assumes continuity. Right? And yet, we do it anyway, and if we take such a picture and such a picture, then more or less, even for the discrete case, the Laplacian at pixels that, you know, just have been rotated are more or less, I should say, identical. And the reason why the Laplacian is such a, well, say, popular tool in image analysis is that it can be used to detect blobs. Blobs, and it does not matter if there is a dark or a bright blob in the image, and by blob I mean a certain circular region. I don't know. Look at me in front of this whiteboard and then drastically reduce the resolution, and you will see basically a certain dark spot and another darker blob, so one dark blob on top of another dark blob in front of something white. So if you were to reduce your mental resolution, you wouldn't see the details of my face, but you would basically perceive it as something rather round in front of something else. This is the kind of blob I am referring to here, and the size of these blobs, so if we compute a certain Laplacian, does depend on, say, 2 sigma. Here we understand again that we have, when we computed G, already smoothed it. Smoothed it with a certain sigma, and then if we compute the Laplacian of G, it will produce rather large or rather low, positive or negative values for either dark or bright blobs of a certain extension, spatial extension, sigma. So that is somehow the radius of the blob or the circumference, I don't really know. Doesn't matter. And I don't have to go into details as to why that works, because that is something we discussed in our first course on image processing. And then back then I already said that there is that this Laplacian is somewhat tied to Gaussians, and right now we will make that more precise. And there is a guy called Lindbergh, and this goes back to 1994, who is, I don't know, say the world-leading expert on what happens if you scale a digital image, so you increase or decrease the size and resolution. And he proposed to consider a scale normalized Laplacian. And by that I mean we look at this function delta norm of g, x, y, and sigma. Now it really pays off that we finally use the sigma as a variable of the function, and this is just defined as sigma times g, right? Too generous of my parentheses here. Sigma times g xx plus g y. I shall call this equation 1. And the idea is to consider this slightly modified version of the Laplacian to detect blobs. That is local maxima or minima of this Laplacian with respect to space, that is to say x and y, and what is different here is and scale, that is to say sigma. By that I mean that given the notion of the Laplacian we have studied up until today, of course we can compute it for an image, and we can look at maxima and minima in the resulting image if we assign this value to every pixel in the image gives us a new image. Can look for maxima and minima there and detect blobs. If we multiply this with a certain sigma, then we can do all this for different choices of sigma and stack these images on top of each other, and instead of a two-dimensional response structure we would then have a three-dimensional response structure, and in that we could look for maxima and minima, local maxima and minima, and I would actually say, yeah, here is a small blob, but that one is actually included in a larger blob, and the real size of that blob is some sigma, right? And I will come back in a second. Now, let me speed this up a bit, because this is all good to know, but right, we're not quite there yet. Here's something I want you to note, and this has nothing to do with image processing. Note, this has to do with physics, and so I'm just dropping it in front of you. There is this notion of the diffusion equation. And I'll just write it down. d sigma g is 1/2 Laplacian of g. So this has nothing to do with images. This is an equation that plays a very important role with respect to certain phenomena in nature. Typically, this is written down as a differential equation with respect to t, but in our case the third parameter is called sigma. T time, here it is sigma. So you will hardly ever find this anywhere. So I'm emphasizing it. And let me call this one 2. Again, this has nothing to do with images, but it typically holds for Laplacians. So, why not just assume that it would work for images as well? So therefore, if we now plug equation 2 into equation 1, we get that delta norm of G, which was defined as sigma delta G, so that was our definition of what that is. And now we'll just solve this equation for delta G, and we get 2 times sigma times the derivative with respect to sigma of G. Okay, and because it is nice to have it all in front of us, I will make use of the remaining white space here. And now we will sort of do the transition from the continuous case to the discrete case ever so brutally and briefly. If we do this, let me say, so looking at this equation here, so we can sort of now think of the normalized Laplacian also being expressed as the derivative of G with respect to sigma, the parameter of the Gaussian. We look now at a discrete approximation. And that would give us delta norm of G, and this time I'm using the square brackets for pointing out that I'm talking about a discrete function now, rather than a continuous one. And we can now express that as 2 times sigma. This is the 2 times sigma, I just took it from here, put it there. And now we sort of have to come up with a discrete analogon of the derivative with respect to sigma. I'll do it like this. G of x, y, sigma plus delta sigma minus G of x and y, sigma minus delta sigma. All of this divided by 2 delta sigma. So that is just a difference approximation of the differential here. Note this trick I made. When we typically do this, we would have, say, G of x, y, and sigma minus G of x, y, and sigma minus delta sigma. But here I've actually added something to the sigma and subtracted something from this sigma, and therefore I have to sort of divide that by 2 delta sigma. I just do this to get rid of the 2. Right? That's and if this becomes really, really, really small, it doesn't matter anyway. Right? It just doesn't matter. So there we are. You now put that here. I can say therefore, the difference of Gaussians, I should make this a large one, Gaussians, DOG, approximates the Laplacian of Gaussians. Laplacian of Gaussians. And again, see our first course where we already discussed that. So image processing 1. We already looked into that. By difference of Gaussians, I mean that, look at this. So G is a Gaussian smooth image, smooth with a certain distorted sigma. Here we have another Gaussian smooth image, smoothed with another distorted version of sigma. And here we therefore have the difference of two Gaussian smooth images. And this is the difference of Gaussians. The difference between two images smoothed with the Gaussian R is called the difference of Gaussians. And we just saw that we can think of this as an approximation of the normalized Laplacian, which requires us to compute the Laplacian of a Gaussian smoothed image, which requires us to compute second derivatives, right? But this one does not require us to compute any derivative whatsoever. We just smooth the image twice and subtract the two results from each other. And that, of course, is computationally slightly less intensive than if we were to compute these second order derivatives. And this is why people like this. The second order derivatives in the Laplacian are actually what detects the blobs mathematically, right? So that is the correct way of doing it. But we can approximate the one by the other. This one is easier to compute, and since this one approximates this one, we can use this one to detect blobs. That's all there is to it. Right? But that was our part of the lecture for today that is, as they say, well founded in theory. Now we move on to something that I have to be very careful because of being on film. I would rather call a heuristic, but some people, most people would beg to disagree. We will now study the idea of Sift. You will likely have heard of it, right? Many of you I know have taken a similar course. Well, if not, then we'll go through this anyway. And I hope that I can add additional insights. This is an acronym for Scale Invariant Feature Transform. Feature Transform goes back to Lowy, who wrote about this, I guess, for the first time in 1999. And this is not just an algorithm or a technique, but a framework of integrating lots of techniques in order to achieve, first, interest or key point detection, and second, make use of the detected key points or interest points to characterize the image from which we have computed them so as to further process the image. So this is a pre-processing step in image analysis, which itself consists of two steps. And it makes use, extensive use, I should say, of the idea of the difference of Gaussians we just discussed, and we saw that it can be used to detect. I did not really see that, but saw it, I don't know, a couple of months ago, and now I just mentioned it, but the difference of Gaussian really detects blobs. Now the question is, what can we make out of that knowledge? So Lowy proposed this framework, and it consists of two major ingredients. The first one is to locate key points. And whereas in our last lecture we looked at how to locate corners and understood the corners of key points, now, given what we have discussed so far, we will look at key points in the sense of they indicate blob-like structures in an image. And the second step, once we have located those key points, is to compute local Sift features. This is how they are called. And by now we also know that when I am talking about a feature, what I mean by that is a certain derived measurement. And by derivation I am not referring to calculus, but that can be any computation we do with a given set of numbers. Could be, for instance, the mean value of a set of numbers is a feature of that set of numbers. The smallest number is a feature of that set of numbers. Right? They are, instead of having to look at the whole collection of numbers, in our case the whole collection of pixels, which is just a collection of numbers, distributed over a grid of coordinates, but instead of having to look at all of them, which is a huge amount of information, typically in image analysis, the idea is it possible for us to throw away a lot of that information and keep the most important things, something that is really characteristic, such as, for instance, the mean value. Maybe we don't need all these numbers, it's just enough if we compute the mean value as a feature of all these numbers and then take it from there. Do more interesting things with just one number instead of 50,000 or whatever. Features. And we will see that features typically in image analysis are really rather involved. That will be one of the take-home messages of today. Now let us look at these two steps separately. First, how did David Lowy propose to locate key points? Why would I actually single out this Sift approach? So last time I singled out the Harris approach to corner finding. Now I'm singling out the Sift approach to blob finding. This is just because for each of these problems, finding corners and finding blobs, there is a whole plethora of algorithms out there, numerous algorithms that do that. But when it comes to corners, the Harris one is certainly the most popular one. Popular because it is really, really simple. I hope we can agree on that. It's actually not that simple, but compared to the other ones, it's really simple. That is why we talked about the Harris corner detector. Today we're talking about the Sift approach, and this is because when it comes to, detecting blobs, and then actually compute something from the local area in the image around that key point, this Sift approach is by far the most popular one out there. There are numerous variations of that, some that are faster, some that are more robust, yada yada yada. But really this one is the most popular, and not because it is the simplest one, but it works really, really well. So the last thing we discussed, because it is the simplest one and therefore very popular, what we discussed today is it is really popular because it works so well. And yet, I should probably warn you already, I might be poking fun of all of this, what is to come. And I should not. I should be neutral about this, but sometimes this is hard for me. I already said that this is basically a collection of heuristics. Other people say, no, what is to come really makes sense, and it is biologically inspired and cognitive adequate. That is to say, all the stuff I'm going to write around in a second is actually what the brain does. I don't know. We will see. And all of this is particularly hard for me. So today's lecture has always been hard for me because I'm not one of the believers in Sift, and there are more believers out there than non-believers. I'm one of the few non-believers. But in the year 2015, things have again changed dramatically. What we are going to learn right now might already be obsolete. I'm really sorry about that. The good thing is you learn, you know, what people have done when it comes to analyzing images, but neural networks are back with a vengeance. And I said, you know, Sift features. There is some sort of derived measurements from the image that characterize certain properties of the image. And what is going to come has been designed by a human brain. Lowy had thought about this for quite some time, came up with a really well-working idea. But for about 2 years now, things have changed dramatically in that the neural networks are back. Something that was very, very popular in the late 70s, 80s, early 90s, and then some sort of disillusion set in because this technique of neural learning did not hold up to all what it promised. But now with the improved hardware we have available, especially with, you know, this powerful graphic cards for linear algebra processing, people have finally sat down and implemented the necessary algorithms for neural network training in an efficient way on graphics cards. And hardly a week goes by now. It is really horrible because I'm sort of closely following this for more than a year now. The shift in trend set in about 3 years ago, and about a year ago I began to worry about what is going on. And now I've been following it for quite some time right now. Hardly a week goes by that I don't read anything where they say, now a neural network can do this, bang. And then they show you, I don't know, examples from the area of image analysis, where you would say this is human level performance. Because nowadays these things are so powerful, because we can now work with them on the graphics cards, have become so powerful that they don't need features. They don't need man-made or human-designed features, engineered features anymore. They learn them by themselves. Feed them 1 billion of images and wait a week and see what happens. Bang. And so I, as a non-believer in the idea of feature engineering, as it is also called, I feel vindication. Right? So I may be poking fun of this, and I shouldn't be warned. Don't you know, take it to this. It's just my personal point of view. But now, without further ado, let's go into that. I'll actually split the computation of key points into 2 parts. So I have 1.1, locate key points. Which is to say, this is in this Sift approach is basically to say, to determine blobs, or the location of blobs, I should say, on different determined blobs, on different scales. There might be larger and smaller blobs in the image, and we want to find them all, not just a certain size of blobs. Right? Well, given what we discussed earlier, we can, I don't know, easily convince ourselves or believe that if we compute smooth images for different choices of sigma. And I am, you know, how to choose the sigmas. Let's not delve into these details. If you really want to, you can actually read it on Wikipedia. I guess this is such a standard approach by now. All the details I am not covering, you can easily look up somewhere on the web. Just Google for it and you will find stuff. If we have computed many smooth versions of an image, we can of course compute difference of Gaussians from, say, 2 consecutive smooth images. We choose sigma to be 1 and choose it to be 1.2. Can compute the difference of Gaussian between the 2 resulting images. Then we have sigma 1.4. We compute the difference of Gaussians between the 1.2 image and the 1.4 image. So we compute the difference of Gaussians for consecutive images, right? And then we stack approach stacks these images, stack the response images, and by this I mean the DOG images. And by this I mean we will get a data structure that looks like this. Each of these planes is one DOG image. And once we have this, and typically this is, I don't know, what is it, 24 DOGs deep, because the different sigmas are, I don't know, typically 25 different choices. I really, I would have to look it up myself. Once we are given this data structure, we determine maxima and minima in the 26 neighborhood, and this is to say a neighborhood that consists of 9 plus 9 plus 8 pixels. Neighborhood of each pixel. I don't have to write this down, right? So let's say in this situation there is one pixel here. It has 8 pixels surrounding it, and in the plane on top of it there are 9 such pixels, and in the plane below there are also 9 such pixels. So this is the 26 neighborhood of that pixel in this three-dimensional data structure, in this stack of images. And now the biological adequacy sets in and my poking fun of it. So, so far so good, right? This is, you know, like, sounds great idea. But now it turns out that if we look for maxima and minima, in the sense that they are the locally largest or smallest point in this stack of DOGs, this will find too many maxima and minima. So we therefore discard edge pixels. Right? And this can, for instance, be done considering the Hessian. So that from the Hessian matrix of each point, each pixel I should say, we can determine whether the pixel lies on an edge or not. I find this highly dissatisfactory because first we say we don't want to have second derivatives because it's so expensive and therefore we compute DOGs, and now we need the Hessian anyway. Just to get rid of the spurious maxima and minima here. Nah, I don't like it. Goes on. We also discard low contrast pixels. Which is to say, a pixel may be a local minimum or maximum in this representation, but it may be a pixel surrounded by rather many pixels of the same intensity. We're not talking about color images, just intensity images. Or it may be slightly larger or smaller than all the, like the local minimum or maximum of all these pixels in this representation here. But all the pixels are really rather bright anyway. And it just so happens that the one in the center of this local is, you know, slightly brighter. So it has a low contrast. We get rid of this. You know, up until here, this was really beautiful, I would say. You know, because, you know, it's going to make sense. And now all these heuristics set in.
Actually,
yeah.
If we discard low contrast pixels, and we are potentially losing the local maxima and local minima. For example, if we have flat plateau or something, we discard all of them, then we actually discard the blob.
Yes, we do. But again, this happens on many different scales. So you smooth the image with a very small sigma. You don't really smooth it, hardly smooth it at all. You smooth it with a slightly larger sigma, and an even larger sigma, and that continues for lots of choices of sigma. And I guess it was in lecture 18 of image processing 1, I'm actually showing what happens if the sigma becomes really large. Because in that situation, a whole region where there might be lots of tiny blobs, if we smooth it with a really large sigma, the whole region becomes a blob by itself. And that is likely more salient, that huge blob, than all the tiny blobs being part of a larger blob. Right? So this is actually done on purpose. This is done on purpose. What we get from all of this, let me put this here, is a set of key points and I will squeeze it in here, but I'll squeeze. So it's a set of key points, and let me just pretend to number them where I ranges from 1 up to n. So doing this, we find n key points, and of course, as always, they have a spatial coordinate xi, yi, but from looking at these 26 neighborhoods, not only do our key points have a location, but they also have a scale. So therefore, the third parameter of these key points is called sigma I. Right, because this is, say, the x direction, this is the y direction, and this is the sigma direction. And if we would find this point to be a local maximum or minimum, then we would know, okay, it has a certain x and y location, but it also has a certain sigma coordinate. So the key points we get from this are indeed three-dimensional. It doesn't stop here. We now have to look into 1.2. And even though I am making fun of it, mainly because of these ingredients, and there will be more like these, it is a good idea. It is really a good idea. In particular, the next part, once it has been done, you would say, okay, everybody could have thought of that, but not everybody does. So, 1.2. Indeed, the recipe up until now is not that remarkable. That is, people have done something like that prior to this. But what comes next really distinguishes Lowe's approach from what people had done so far. Because we now determine the key point orientation. We have points that have an x and y location and a scale sigma. Now we are interested in, do they have a direction? Let's see what that may mean. So, for each key point, and right now we just look at the spatial xi, yi coordinate, we consider the smoothed image at scale sigma. So if you ever have to implement this all by yourself, don't throw away the smooth images you used to compute the difference of Gaussians, right? You're given an image, you compute 26 or so smooth versions of it. Don't throw them away. Keep them for this step. Have an image, compute 26 smooth versions of it. From that you compute a 25 difference of Gaussians. There you locate key points and their scale. Once you are done with that, you look at the locations of the key points and their scales, and in the correspondingly smooth image, you do the following. You compute gradient magnitude m at this point. Let me write it like this, xi. So this is x and y, but I don't know. Gradient magnitude and orientation. So of course, thinking of this requires us to derive each of these smooth images. So the computational burden increases. But we can compute gradient images ddx, ddy for each of these images. And then the corresponding key points in this derived images, we compute the magnitude and the direction of the gradient. Of course, we do not have to derive the whole image. You can do that locally, yada yada. But you know, it becomes less elegant. Once we have that, so we do this in a neighborhood. Of this key point xi, which I write as an abbreviation of xi yi. In a neighborhood, that means not only do we need the magnitude and orientation for this particular pixel, but like if this is the pixel for a couple of pixels, I don't know, say whatever, 16 by 16 neighborhood of pixels surrounding that one. In this 16 by 16 neighborhood, we have to compute the x derivative and y derivative. From the x and y derivative, we can compute the magnitude, length of the gradient, and the orientation of the gradient. And we store all that in a histogram. Let me therefore continue here. So once we have that, for every pixel, mind you, right, this has to be done for every key point, not just for every key point. We have to do the following. Compute an orientation histogram. I shall call it H of theta, and it has 36 bins of 36 bins. And now, fun again, very biological, right? No, seriously, damn it, I have read so many papers and textbooks about how brilliantly biological all of this is. Come on. Why 36? Right? This has nothing to do with biology. Next thing also, right? Before we compute this histogram, what we actually do is we smooth this local patch. So we have this key point, and then there is this local neighborhood. And in this local neighborhood, we compute the gradients, and from that we get their magnitudes and orientation. But before we do this, we even center a Gaussian at the key point. Center a Gaussian at this point xi, yi of with 1.5 times sigma I. So we smooth it again, you know, to be more robust against noise. And once we have done that, we then finally compute or weight. We weight each. Each orientation theta of xi by its magnitude. Its magnitude compute m of xi, and then compute the histogram. Then compute the histogram. So by 36 bins, I can of course tell you where the 36 come from. This is 360 by 10, right? Over 10. This is where the 36 comes from. We have, if we were to go for degrees, 360 possible choices of where a gradient could point towards. And then instead of going for 360, we bin each 10 of them into a bin. That gives us the histogram of 36 bins. Prior to that, we actually smooth the image again and get these directions, and we multiply each direction sort of by its magnitude and count these weighted directions in the histogram. And what that gives us is probably something like this. So for a point xi, we get a histogram, 1, 2, 3, 4, and so on, 36 bins, where, I don't know, not many pixels have a direction between 0 and 10 degrees, 36 degrees, 10, yeah, 10. But probably a lot of pixels have, I don't know, pointed in a direction between 10 and 20 degrees, whatever, and you get something like that, a histogram of how many pixels have a gradient that points in a certain direction, and how sort of strong was that gradient, and we sort of factor that in the height of count here. And looking at that, we would then say the dominant direction here. The dominant direction is this one. So locally, for that key point, most of the gradients in the neighborhood about that key point have an orientation between 10 and 20 degrees. So that is the direction of the key point, or the orientation.
In case of images, I think we can even reduce the bins, because we have, I guess, 8 directions of gradient, right?
Yeah. You refer to symmetries with respect to sign.
Not really. I'm just thinking, for example, we are calculating gradient, and gradient is actually the direction of steepest ascent or something. So we can have steepest ascent to right pixel, or the corner pixel, up pixel, and this way. So direction will be just 8 or something.
No. Well, of course, but sure, you can simplify everything as much as, say, humanly possible, right? So once again, the situation is like this. We have an image, and there is a key point somewhere, and we do have to compute all the gradients in a neighborhood. So there might be here, 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 and there's nothing, and whatever. This actually is not what we are doing here. Is not so much just looking at the gradients related to that point, but all of its neighbors. And of course, you could say, well, it just points up, there, like north, northeast, east, southeast, west, southwest, or whatever. Sure, why not? You of course lose. It's a feature. It's a feature. Like these histograms, for instance, are features of what is going on in the neighborhood of the gradient. You throw away a lot of information. And I cannot even argue against it, because I would never defend the 36. That would be ridiculous. Yeah, sure, you can. I don't know. Maybe it doesn't work as well, and so you have to experiment a lot. What parameterization of the approach gives the best results in practice. But of course, best results in practice refers to, well, let's see if we can get robust recognition of key point. Can we find this key point in this image? Can we redetect it in another one? Stuff like that. Lots of experimentation necessary to identify the best parameters, or you are rather generous with your choices, like 36. It's not so much, but it's not too few either. Can expect that it will work. This has nothing to do with science. This is called feature engineering for a reason. People play around with, what if we did this and then that and here we have 3 possible parameters or levers to pull and whatever. And after lots of experiments by poor PhD students, we find that this sequence of operations with this set of parameters works. I don't like that. And I am sort of happy about the success of neural networks because sort of they abolish all of this. Let's see how long this wave will last. Of course, nothing is forever in this area. So in a couple of years, neural networks will be out again. Let's see. Really, I cannot defend any of this. The choice of 36. What? The peak, which I just erased, the peak in this histogram indicates the local direction. It said, okay, the dominant direction or the dominant gradient orientation is a characteristic of this local image patch. Of course, it may be that there are several peaks. If there are several peaks of more or less the same height, then we simply clone the key point, that is, we duplicate it, clone the key point, and assign each one, and assign each clone one direction. Right, this histogram may have several bins which are very high, where we have counted a lot of contribution, and maybe they're even actually of exactly the same height. Then which one to choose as the local dominant direction? The solution here is we don't choose. We sort of copy the key point, and one gets this local direction, and the copy gets that local direction. Right? So this actually produces, therefore, all of this, the operations in 1.2, a set of key points with scales and orientation. So that is to say, here we are dealing with a set of points xi, yi, sigma I, and theta I. And the I ranges from 1 up to some capital N now because of the cloning. This may actually be a larger set of key points than the one we had computed in the previous step. And now, let me really quickly just go through the last part of that, and then let's talk about applications next time. All right, we now have key points. This is cool, because if an image is large, I don't know, 2048 pixels by whatever, 1500, lots of pixels, tens of thousands of pixels, this may produce a couple of hundreds of key points. So instead of looking at the image as a whole with tens of thousands of pixels, we have now singled out certain locations in the image, and for some locations we may have also singled out a couple of different scales and different orientation, or whatever. This set I just erased typically contains of the order of 100 or 1000 points, which is much, much less than the number of pixels in the original image, right? And we can therefore understand it as a way of information reduction, or say compression, or as a way of identifying what really matters. If we subscribe to the idea that blobs are really salient and that it is good to find them and to actually sort of identify how large they are and what orientation they have. We probably could actually continue computing with these 4 numbers for every pixel, but it is better to compute more advanced features for every such key point. And so therefore, the second step is to compute the descriptor, Sift descriptor, or feature. And this works like this, very biological. So we consider a 16 by 16 pixel neighborhood. About xi, yi at scale sigma I. 16 by 16 is certainly what your brain does. And then we smooth it again. We smooth it using Gaussian of width. What do we have here? 0.5 times sigma I. And we compute gradient magnitudes. And orientations. You might be tempted to say, "Hey, we have done that already," but no, we have to do it again. Right? We already did this with a Gaussian. We have this neighborhood, and we smooth that with 1.5 times sigma I, and now we do it with 0.5 times sigma I. Don't ask me why. I really don't know. Right? And I will now erase this. Try to squeeze everything. So let me draw a picture. So this is the local neighborhood, or 16 by 16 surrounding our key point at some scale. Right? We have lots of scales potentially, and here we consider. Now I have to subdivide it even further, right? Basically 16 by 16, I really don't want to. This is a 16 by 16 pixel grid surrounding that key point, and we smooth this one using a Gaussian. So this is what the circle indicates. This is sort of the two-dimensional Gaussian we use to smooth this. And now, for each of, let me, I don't know, so this is a 16 by 16 grid, let's just say, so, these are indeed all, I'm just showing one cell here, but this is 16 pixels, so we have 4 pixels in the x direction, 4 pixels in the y direction, 4 each of these 4x4 cells. Right? And indeed, the Sift descriptor is computed with respect to each of these cells. Let me single out one of them. In these cells, we compute. So for each 4x4 subcell of the neighborhood, we do what we just did in the previous step. We compute a weighted orientation histogram. Just as in the previous step, of 8 bins. There you go. Of 8 bins, and normalize. It's horrible. I'll write it down as I have it here. And normalize it. So that is to say we make it sum to 1, and after that we threshold it, and threshold it at a value of 0.2, that is every bin in this 8-bin histogram, which after normalization has a value of less than 0.2 will be set to 0. If we do that, then this histogram does not represent a probability distribution anymore, and so therefore we normalize it again, and normalize it again. And normalize again. Woohoo. So, I shouldn't do it, but you know, it's, my lecture. So, if we do this, what we get is something we can picture like this. Let me just, I don't know, some of this. So, 1, 2, 3, 4, 5, 6, 7, 8. These are tiny arrows pointing in 8 directions. Right? This is the result for the first 4x4 grid. We can of course do this, I don't know, for the second one as well. Maybe it looks like this. It's like little flowers like this. Flowers of, we can understand as you know, collections of 8 directions, and scaled by how often this direction occurred there. Now, this is a 4x4 grid. Each of these cells contains 8 numbers, as you proposed. So what that provides us is a 4x4x8 is 128 dimensional feature, and I say feature vector for each key point. So therefore, in a nutshell, we may have computed a couple of hundreds of key points out of a couple of tens of thousands of pixels, and for each of the key points we detected, we now have computed 128 numbers to characterize what is going on in the neighborhood of that point. And so therefore we have now turned the image from a set of tens of thousands of pixels into a set of several hundreds of 128 dimensional vectors. And these 128 dimensional vectors are then used in subsequent processing steps, which I will not discuss today, but let's continue that in our next lecture. However, once again, I make fun of this, right? And this is, maybe I should say, I make fun of the marketing behind all of this. Because really, if you read the disciples' literature, so there are people out that this has been used with tremendous success for over 10 years. After it was proposed, people, Lowy originally proposed this to solve the following problem. Actually, that was done to automatically create image mosaics, something we studied in the last semester in Image Processing 1. We said, okay, we have a couple of images taken, I don't know, either in a rotated fashion or in a shifted fashion. And out of a couple of images, we want to compute one larger image. And that required us to determine geometric transformations between these images. And the problem of determining the geometric transformations required us to identify corresponding points. We did that manually. Lowy wanted to do that automatically. So we had lots of images and wanted an automatic way to very robustly identify, okay, this point in this image, I don't know, say this point in this image is the same as this point in a slightly rotated version of that image. And therefore he developed that and now had all these key points and just has to sort of check which key point in this image corresponds to which key point in that image. Very successfully, because the resulting mosaics just look stunning. So this was where that came from, basically to automatically identify corresponding points. This can of course be used, you know, once it was there, people immediately realized, well, we can use that for database lookup. So there is an image, we compute all its key points, store them in a database, and assign this, I don't know, the label image 1. We have a next image, compute all the key points, store them in a database with the label image 2, and so on and so on. We do this, you know, with tens of thousands of images. And now we have a new image, and we want to figure out, yeah, well, which of the images in our database are similar to the one that we are looking at right now. So let us compute the key points in this new image and, you know, just look up in the database which images contain similar key points and say, well, this image is an instance of image 1 and image 17. It's very similar to image 1 and 17. So not only can you use that for mosaicing as a pre-processing step for mosaicing, but you can also use that for image retrieval. And image retrieval is, of course, like the process I just described. One way of making sense of what is in an image, right? If you have a database of tens of thousands of images, each image labeled with whatever is seen in the image, a dog standing in front of something eating a bone, could be a description of an image. You have a new image, and it is found to be very similar to an image that is labeled with a dog standing in front of something eating a bone, then why not should this new image also show a dog standing in front of something eating a bone? So it's, you know, recognition by retrieval. Once that was realized, a boom set in. People began to use this extensively, really for a period over 10 years, and with tremendous success, right? And when I said the disciples of this approach, it has been used so successfully. You know, people went at great length to argue why this is exactly what the brain does, or that is like so inspired by what the brain does. Yes, indeed, the brain does something like block detection, and yes, indeed, orientations is very important for what the brain does. But this is not what the brain. It does not compute 8-bin and normalize it and threshold it and normalize it again. So I'm making fun of this, and I'm not making fun of Lowy. I'm not really making fun of this approach. I'm making fun of the hype surrounding it. And again, the vindication I feel is that this hype has ebbed away now. It's gone. Haven't read something about this in a while. Right? And this is a lesson to be learned. This is so much easier said than done. All of this area of artificial intelligence as a whole, but all its sub-areas, for instance, image analysis, are subject to hype cycles. Right? Once in a while, somebody has an idea that works really, really well, And then everybody does it, uses it, improves on it. It works even better, faster, more robust, whatever. But then eventually this sobering period sets in where they realize, okay, we can do stuff now we couldn't do 5 years ago, but still we cannot do what we actually want to do. Right? But there are these hype cycles. They are really very, very characteristic. And this is one of the things that was extremely hyped for an extensive period of time, but now has sort of faded away again. The reason why would I then actually, talk about it in the lecture? You might be tempted to ask, well, if this is done, then why do we have to learn about it? That is a really good question. Basically, this is to prevent you from reinventing it. So, in a sense, I have to. What can we do in a lecture? There's so many things out there, and I just have to pick some of them. So I picked the ones that have been used with great success, and even though if they may not be as relevant anymore as they were just 5 years ago, right? But you have to sort of get a feeling for what works with images, what people have done, what actually works very successfully. And look at it. I mean, this is, I consider it ugly. This is such a mess of what has to be done. So many smooth images, then difference of Gaussians, and then this and that, and then once we have then 16 by 16 neighborhoods and smoothing again and gradients again, and then blah blah, 128 dimensions. Oh, I hate it, but this is how it is. Right? Like seriously, making sense of what is shown in a picture automatically is hard. We, to this day, do not know how the brain does it. If we were to know how the brain did it, we could do it on a computer. We can't. We can't. Now with the modern neural networks, it seems as if we're getting closer, but still, even these modern neural networks are not a mirror image of what the brain does. Right? If we knew how the brain worked, we could emulate it on a computer. We don't know that. And therefore people come up with stuff like that. And this is horrible, but it works. It works extremely successfully. And so therefore I have to expose you to sort of what is really out there. Because up until a couple of weeks ago, you may have thought, this is all easy, it's just this and that and blah, and here and there, threshold and whatever. It is not. The real stuff is this. This is what people use to make sense of what is in an image. Well, let's keep it at that. Next time we briefly look into how that can be used to make sense of images. Are there any questions for today? Great, then we see each other again on Thursday. Thank you.